Hello everyone and welcome back to another video here on the School of Quantum. Today we are looking at Quantique, which is trying to solve the error propagation problem by introducing error correction. And if you want to know how they actually do it, what sets them apart from others, and what is this company all about, then make sure to get yourself something to drink, because we always want to stay hydrated, and stay tuned for today's video. And with that, let's hop right into their website. So here we are on the starting page of Quantique. It says making quantum matter. There's also a nice animation here, which you can't see right now because it has already played. And then if we scroll down, we see this little video clip here. And then going down even further, we see here a setup of a solid state, let's say, probably quantum chip, but actually what we see here is the cryostat, so the cold side of the cryostat. We see a lot of radio frequency cables and so on. And it says error correction remains the main challenge to overcome for quantum computing to establish itself. At Quantique, we focus our efforts on error correction to build fault-tolerant quantum computers that are efficient and useful for a wide variety of applications. We design our systems to correct errors as they occur at all levels of operation. We strongly believe that this is how we will achieve functional fault tolerance to produce useful quantum computers to provide significant benefits for humanity. So they are not only, let's say, working on the algorithm side, as this image here also indicates, as this photo indicates, they're also busy on the hardware side. So the error correction really is supposed to get baked into the system. It says correcting errors on the layer that they occur as soon as possible. So it is not just, let's say, a software layer that is using physical qubits and then running some type of error calculations on top. But there's also stuff happening on the layers below, probably within the qubits itself. Here are some, statements. So the first one is roadmap to fault tolerance. So Quantique already produces groundbreaking results on quantum error correction. We are implementing our ambitious roadmap to reach our goal of releasing a quantum computer with 100 logical qubits by 2028. The point of recording of this video is in 2026, so this is 2 years from now. We expect to deliver a minimum viable product MVP in 2024 and showcase the error correction results of our first multi-qubit system. Quantique will also onboard its first algorithm partner and continue to expand its network of early adopter industry partners. Useful applications for business. Our three-pronged approach offers benefits for industry partners. Our cutting-edge error correction combined with lightning-fast clock speeds and a clear path to quickly scaling up to useful levels make Quantique an ideal partner for early adopters in the material science, pharmaceuticals, and other sectors that can benefit from advanced calculations using deep circuits and complex algorithms. Our solution can help solve challenging problems in design, manufacturing, and operations. Our team is keen to understand specific needs and suggest useful solutions. Then efficient in all categories. Efficient use of resources is central for our model. We have developed a quantum computing architecture with an extremely efficient use of qubits. Fewer qubits means lower energy consumption and a smaller, more efficient system. Quantique is also part of a world-class quantum ecosystem which allows the company to deploy its capital efficiently and still have access to the highest quality labs, equipment, and talent, as well as chip production facilities. And then here we see somebody in a clean room suit, some very close up of a cold tip, of a cryostat, some software development happening here with code in some list JSON files in the background and some graphs and some, let's say, silicon design. So we see somebody in this clean room suit and also the theoretical side on the whiteboard. So they really cover, let's say, the whole value chain from processing all the way up to the theoretical physics and, let's say, programming side. Technology at Quantique, we focus on quantum computing error correction. We dedicate our efforts to developing fault-tolerant quantum computers to bring this cutting-edge technology to market and shape a future where everyone benefits from quantum innovation. World-class quantum error correction changes everything. Quantique is at the forefront of the field of quantum error correction. Quantum computers developed with our unique approach to correct the most common types of errors, bit flips and phase flips, using bosonic codes. Unlike other designs, we correct most errors without dedicating overhead of redundant qubits to error correction. Most of our qubits are thus actually used to perform calculations while achieving a fault tolerance level that allows the delivery of useful applications while reducing between 1,000 and 10,000 times the number of physical qubits required by various other quantum computing models. So there's a lot of information in that. I just want to, let's say, note a couple of them. So bit flips is very similar to what you know from classical computing. So think about a chip where you have classical information in there, ones and zeros. Now, every once in a while, it can happen that even in your storage of your computer, a bit can flip from a 0 to a 1 or from a 1 to a 0. That can, for example, happen when a particle, a high energy particle from space, hits your computer or your chip at the right spot. Then this can flip. And this is what is called a bit flip error. Now, for the phase flip, it's already a little bit more intricate. This is something which is very unique to quantum information. So if you think about the qubit, there are of course different ways to build a qubit. But let's think about one which is just encoded in a spin. So a spin is a property of a particle or a property of a quantum object. Like, for example, think about an electron, and the spin can point up or it can point down. So when you measure it, you will either find it up or you find it down. But in fact, the state that is describing this spin is much more complex. So it can also have positions in between. So you can put it in a superposition of 0 and 1. So it technically sits somewhere in between. And when you measure it, it will still give you a 1 or it will give you a 0. And depending on the position that you put it in, the probability of giving you a 1 and a 0 will change. Now, if you, for example, do a specific gate, like a Hadamard gate, then you're rotating those qubits. And now, if you, for example, have a phase flip, that can create some error in this phase that you're introducing, in this kind of tilt of your qubit that you are creating, and thereby it creates a change in the probability at which you measure the final state. And of course, if you entangle this qubit with many others, it kind of spreads the error across the whole superposition state that you are creating. So that's more or less the types of errors that we are looking at here. And then usually the way that you can kind of cope with this is by basically taking a lot of qubits, and then you have some additional helper qubits which you don't really use to store the information, but you kind of bring them in a known superposition towards the state where the information is inside, and then you check back for this helper qubit if it's still in the state where it's supposed to be, and that way you can kind of know if there's an error that happened or not. And these codes, they can actually they're called surface codes because they're spreading across the surface of your qubits, and they can actually become quite complicated. And I'm not an expert on that, so I'm not gonna try to aim to tell you any details about that. Just saying they can become very complex. It's a completely own theoretical area, and it's very unique to quantum systems, because in classical systems you don't have this idea of entanglement. You cannot connect the classical information storages with each other in that way. And therefore, it is very much a quantum thing, and it's very much a research thing. And the claim here is that by doing it with this bosonic codes that they are using, they have less of this overhead because of this bosonic encoding. Quick note on bosonic. So there's fermions and bosons in quantum physics. These are two fundamentally different types of particles, and bosons, they are, let's say, indifferential. They cannot be differentiated. They can all be somehow connected to each other or similar. And for fermions, this is not the case. And when you, for example, look at superconductors, this is when two electrons kind of by a Cooper pair up and then become like a bosonic state. So there is also some reasoning behind calling it like this. This is just the long story long. Then it says fast processing for solutions. Now our superconducting quantum computers perform at clock speeds required to perform calculations and deliver insights to users in a practical time frame. Users who must perform advanced calculations using deep circuits and complex algorithms will be pleased by how quickly computations are completed. Our approach is designed to make quantum computing both accessible and practical for large industrial and government users who need to run their calculations quickly and extract reliable insight from the data. So quick information extraction from that. So they're using superconducting quantum computers, which is also something that we kind of had some indications on before by looking at the way that they show the quantum computer, right? It's a solid state system. Now we know it's a superconducting one. With that comes a high clock speed. This is high as in compared to, for example, systems that have to be manipulated optically, like ions, for example, where you have to excite them to different states and wait for them to decay, or like physically shovel atoms or ions back and forth. That takes a little bit longer time, and in comparison to a superconducting system, it's a bit slower. Comes at other advantages, of course. And then they're also talking about these deep circuits. With deep circuits, they, I think, mean that you can apply a lot of gates after each other. So you can create a sequence of multiple gates. And then, of course, you can do that quicker here because generally this whole system operates usually at radio frequencies. So you are talking about gigahertz pulses that you are triggering here. Then it says a clear path for scaling to fault tolerance. Quantique is working to quickly scale its quantum system to high fault tolerance levels to deliver a 100 logical qubit machine by 2028. The goal of a shorter path to useful fault tolerance can be achieved by combining few errors with fast calculation speeds without requiring massive overhead of redundant qubits for error correction. This more readily allows a reliable operation of useful quantum computers with a wide array of industry applications. And then there is something here about the people meet the faces, minds, and hearts behind Quantique, a team united by a shared vision of quantum excellence and a commitment to redefining what's possible. Then it says our impact, Quantique's pioneering work in quantum error correction has garnered attention from corporations worldwide seeking practical computing solutions for everyday operational challenges. And I'm recording this beginning of 2026. So we can see this is pretty much up to date because the last one is from mid of December 2025. It says Quantique receives 23 million US dollars in non-dilutive funding through Canadian Quantum Champions program. And quick note on this, this series is called the Hidden Quantum Champions. So similar to the Quantum Champions program, just hidden. And if you want to watch more of those kind of videos, make sure to check out our YouTube channel. In there we have a playlist called the Hidden Quantum Champions playlist. In there you can find many more reviews of similar or other companies from the quantum space like this one here. Then we are reaching the end of this first opening side. We see the companies based in Canada, in Quebec. Now quickly on the technology, we already saw they are using superconducting qubits. It says at Quantique we focus on quantum computing error correction. We dedicate our efforts to developing fault-tolerant quantum computers to bring this cutting-edge technology to market and shape a future where everyone benefits from quantum innovation. Here we see some silicon probing system or microscope. Looks a little bit like where you clamp those wafers for evaporation. This I think we've seen already, and then there are some more nice pictures here of the system. It says we're constantly reviewing the global quantum computing landscape, and we truly believe that Quantique has one of the most promising technical roadmaps to realize fault-tolerant quantum computing. The rigorous support they receive from the world-class Sherbrooke quantum ecosystem is key in helping them compete against the tech giants of the world, says the deep tech venture fund at DBC Capital, which is, I guess, supporting them. To deliver their potential computing power exponentially greater than conventional computers, the systems inside quantum computers must operate in a quantum state to leverage quantum effects. These states are very delicate and often last only a fraction of a second. Depending on the machine's design, these quantum states must be generated at temperature close to absolute zero. This is, in this case here, for the superconducting properties of the qubits, of course, required, but also generally in order to reduce the thermal noise, right, that is acting on the qubits. Changes in temperature, magnetic field, electronics used to control qubits, the bit on which quantum computers operate, and a host of other factors can all cause noise, various types of interference with these quantum states, which causes errors on a significant number of qubits. To address this, many quantum computer makers dedicate additional qubits to correct these errors. This redundancy helps ensure the quantum state remains intact long enough to perform the required calculations. It should be noted that a faster quantum processor means the calculations can be performed more quickly, which in turn means that quantum states do not need to be preserved as long when using a quantum computer with faster clock speeds. Designing quantum computers in this way can mean devoting 1,000 to 10,000 qubits to keeping just single qubit function correctly. We can imagine a system with 10 million qubits could only barely use 1,000 qubits functioning correctly in a state with the balance dedicated to correcting errors. That's not a very convincing approach, right? We fully agree. Rather than using this brute force approach where millions or even billions of qubits are required to control a much larger number of error-corrected qubits to deliver on the potential of quantum computing, a new way to thinking arose to look for better ways to preventing or correcting those errors. That's how Quantique was born. A different approach, proven results. Quantique is a startup spun off from the University of Sherbrooke's renowned institute Quantique in Quebec. Our goal isn't to take on the big tech companies building large-scale quantum systems. Our co-founders, Julien Lemery and Philippe Saint-Jean, I guess, I'm not sure, rather chose to set out to design a much more efficient system. Our approach aims to reach the goal of a fault-tolerant quantum computer using fewer qubits, a machine that is more efficient and therefore making the system easier to control and scale. First error correction protocols on a single bosonic qubit had to be designed. Those protocols correct the two most common types of errors in quantum computing, known as bit flips and phase flips. the company's latest results indicate that they are able to effectively reduce errors in this way by 14% on a single qubit without needing to dedicate any additional qubits to error correction. The road ahead. To this day, we are the first company to produce such results at the individual qubit level. In fact, we are the first company anywhere to be able to reduce errors in a quantum system without using dedicated redundant qubits to do so. Our approach puts us on track to develop lean and efficient quantum computers, smaller and far less complex to scale up to a size at which they are more likely to offer an advantage over classical computers. We intend to demonstrate our first multi-qubit system and publish results from that initiative in 2024. Primarily, simulations suggest the probability of likely additional synergies in error correction when adding additional qubits beyond the existing single qubit in Quantique system. This means Quantique has a clear path to building a useful quantum computer that won't require thousands or 10,000s of redundant qubits dedicated to error correction. By 2028, we will build a 100 logical qubits quantum computer in which each logical qubit is implemented as a single physical qubit without the need for any form of material redundancy. And that's, I think, something very interesting. So the idea is to build something that is lean and error corrective. This is something different to the error mitigation. That's maybe also important to note here. So we have heard of error mitigation before. This is when you, for example, try to tune your qubit. You collect a lot of data about how this solid state qubit is behaving, because one difference between a superconducting qubit and, for example, an ion is that superconducting qubits, they are big systems, right? They are micrometer size big. So they consist out of many atoms. And therefore, they always have a little bit of a different property, which is different from ions, where every ion is exactly the same, right? By the way that nature is designed, ions are always the same. And these superconducting qubits, they're always a little bit different. And now you can kind of cope for this difference by actually tuning them. So you do a lot of measurements before you collect all the properties of the qubit, and then you understand, okay, I need to adjust something a little bit here, I need to change something there. This is then error mitigation. So you're basically using statistics, you're using knowledge that you acquired about this qubit to kind of reduce the number of errors, which is not the same as error correction, where you are actually tracking those errors and correcting them. And that's what they are aiming here for, what Quantique is aiming for. They're using this bosonic code to remove errors, bit flip errors and phase flip errors from the computation. With that, let's quickly check out the people section. So meet the faces, minds and hearts behind Quantique, a team united by a shared vision of quantum excellence and a commitment to redefining what's possible. And then here we have a list of the different people within the company. I think here we have the founders, right? So let's quickly open that. And yeah, we then see the name as well as, okay, what is their background? So physics background, and also quantum physics, quantum optomechanics background. So both very much people that understand the fundamental physics side of things here. And then, of course, there's a whole team with various different backgrounds. So we see here we have people with microwave design. So we have theoretical physicists and many more, nanofabrication. So all the different skills that you need to actually build such a machine. Finally, there's something here on the impact, and I think we've seen that before. So there's this note on the fund here, quantum leadership and the economics of discovery, and so on and so forth. So a lot of news articles to explore. With that, I'm closing again today's video. If you liked it, please make sure to leave a like, and also use the hype function if you really like this video. As always, also make sure to stay hydrated, and then see you in the next video. Bye bye.